In this video, we are gonna focus on solving physics problem about Coulomb's law. So problem 1 says two charges, positive 3 microcoulomb and 12 microcoulomb are fixed 1 meter apart, with the second one to the right. Find the magnitude and direction of the net force on a negative 2 nanocoulombs charge when placed at the following location, halfway between the two. So here we have a charge of 3 microcoulomb, and here is 12 microcoulomb, and the charge of negative 2 nanocoulomb is placed. And we know the distance here is 1 meters. So here must be 0.5 meters since it is in the midway. And we also know like repel, opposite attract, since 3 and 12 microcoulombs charges are positive, they're gonna attract the negative charge. So the 3 microcoulomb is gonna apply a leftward force F3, and the 12 microcoulomb charge is gonna apply a rightward force. So F3 apply a leftward force, and F12 apply a rightward force. You can calculate the magnitude of the force by using Coulomb's law. So F3 is gonna equal to Coulomb's constant, so 8.99 times 10 to the 10th power times the 2 charge, so 3 times 10 to the negative 6th power coulomb. So you convert microcoulomb to coulombs, you times 10 to the negative 6th power, and convert nanocoulomb to microcoulomb, to coulombs, into times 10 to the negative 9th power. So now I ignore the negative sign here because I just want to calculate the magnitude over r square, so 0.5 meter square, and you should have a volume of 2.16 times 10 to the negative 4th Newton. And because it's 4-point rightward, so we are gonna put a negative sign here to represent the direction. And now we can also calculate F12, which is equal to the Coulomb constant times the 2 charges, so 12 times 10 to the negative 6 times 2 times 10 to the negative 9th over r square, so 0.5 square. I ignore the sign here because I only want the magnitude first, which is equal to 8.63 times 10 to the negative 6th power. And because the force point to the right, so it gotta be a positive volume, right? So it's equal to 8.63 times 10 to the negative 4th power Newton. Have a SI unit of Newton. Now you can calculate the net force. So net force is gonna be equal to the sum of F3 plus F12, which is gonna give us a volume of 6.47 times 10 to the negative 6th power Newton. So this is the final answer for part A. Now let's do part B. Now the negative 2 nanocoulomb is placed half a meter to the left of the 3 microcoulomb charge. So here is the 3 microcoulomb, here is a 12 microcoulomb, and here is a negative 2 nanocoulomb. Half a meter is 0.5 meters, and we know 3 meter charge is 1 meters away from the 12 microcoulomb charge. Oops. Here is a negative charge, positive charge, positive charge. So the 2 positive charge is gonna attract a negative charge. So the 3 microcoulomb is apply a rightward force of F3. And the 12 microcoulomb is gonna apply a right-wall force of F12. And now I can calculate F3 and F12. So let me move this up a little bit. F3 is going to equal to the Coulomb constant, so 8.99 times 10 to the negative 9th power times the 2 charge, so 3 times 10 to the negative 6 times 2 times 10 to the negative 9th power. I ignore the sign of the nanocoulomb charge because I only want the magnitude first, and then you need to divide this part by R square. So here R is equal to 0.5, so 0.5 square, which is equal to 2.16 times 10 to the negative 6 Newton. And F12 is going to be equal to 8.99 times 10 to the 9th power. Here is 9, sorry I wrote a negative sign here, times the charge, so 12 times 10 to the negative 6 power times 2 times 10 to the negative 9th power over R square. So here is 1 meter and here is 0.5 meter. So it's gonna be 1.5 square, which is equal to 9.59 times 10 to the negative 5th power. So here we have the volume of F3 and F12. Now you can calculate the net force by adding them up. So F net is equal to F3 plus F12, which gives us a volume of 3.12 times 10 to the negative 4th Newton. So this is the final answer for part B. Now let's do part C. So now the negative 2 nanocoulomb is placed half a meter above the 12 microcoulomb charge in a direction perpendicular to the line joining two fixed charge. So here is the 3 microcoulomb charge. Here is the 12 microcoulomb charge. And here's gonna be negative 2 nanocoulomb charge. Right. And here it has a distance of 1 meters. Here has a distance of 0.5 meters. So because the 3 and 12 microcoulomb charge are positive, so they're gonna attract the negative 2 nanocoulomb charge. So here is gonna be a downward force, and here is gonna be a force like this, and this force is F3, this force is F12. So you can use Coulomb's law to calculate the two force. F12 is gonna be equal to 8.99 times 10 to the 9th power times 2 times 10 to the negative 9th. So I ignored the sign here because I want to calculate the magnitude first, times 12 times 10 to the negative 6 over 0.5 square. So let me take the magnitude first, which is gonna be equal to 8.63 times 10 to the negative 4th Newton. But because F12 is pointing downward, so it gotta have a negative sign to represent the direction. So F12 is gonna be equal to negative 8.36 times 10 to the negative 4th power Newton. So this is F12. And now you can calculate F3 first. So here has the distance of 0.5 meter, and here has a distance of 1 meter. So let me write this down. So 0.5 meters, 1 meter. So you can calculate the volume of R here. So R is gonna be equal to the square root R is equal to the square root of 1 plus 0.5 square, which is approximately equal to 1.11. So now we can calculate F3. So F3 is gonna be equal to 8.99 times 10 to the 9th power times 3 times 10 to the negative 6 times 2 times 10 to the negative 9th. So I can ignore the sign here because I want to calculate the magnitude first. Over R squared, 1.11 squared. And this equation will give us a result of 4.3152 times 10 to the negative 6th power has a unit of Newton. And now you can separate F3 into different components. So let me write it here. So here is F3. And you can separate them into the vertical component and the horizontal component. And here is 0.5, here is 1, here is 1.1. So here is gonna be Fy, the vertical component, here is gonna be Fx. And we know Fx is equal to F3x is equal to F3 cosine theta. And we know cosine theta is equal to 1 over 1.11. And sine theta is equal to 0.5 over 1.11. So F3y is going to be equal to F3 sine theta, which is equal to F3 times 0.5 over 1.11. And F3x is going to be equal to F3 cosine theta, which is equal to F3 times 1 over 1.11. Right? So now we can plug in the number to calculate the magnitude of the two forces. So F3x is equal to F3 times cosine theta, which is equal to F3 times 1 over 1.11. So it's equal to 4.315 times 10 to the negative 5th times 1 over 1.11, which gives us a volume of 3.86 times 10 to the negative 5th. So here is the magnitude of the force. And we know because the force is pointing leftward direction. And then F3x gotta have a negative sign here. Right? Why is here the positive one the magnitude? Because here I only calculate the magnitude of F3, but here from force component we know the horizontal component is pointing to the left, so it gotta be a negative volume, and the vertical component is pointing down, so it should also be a negative volume. So this is why F3x is a negative volume. Now you can calculate F3y. It's gonna be equal to F3 sine theta, so which is equal to F3 times 0.5 over 1.11, and this gives us a volume of 1.11 0.935 times 10 to the negative 5th power. And same thing, I'm taking the magnitude here, so it gives us a positive volume, but because we know this is pointing downward, so F3y must be a negative volume. So negative 1.935 times 10 to the negative 6th power Newton. Now we can calculate the net force. So how do we calculate the net force here is you need to add up the y component and then use the Pythagorean theorem to calculate the net force. So the y component is equal to F12 plus F3y, in which give us which is equal to negative 8.36 times 10 to the negative 4th power plus negative 1.935 times 10 to the negative 5th Newton, which give us a volume of negative 8.36 times 10 to the negative 4th power. So this is the y component, and the F component, the horizontal component, is equal to F3x. So F net is going to be equal to the square root of Fx squared plus Fy squared. So it's going to be equal to the square root of negative 8.63 times 10 to the negative 1st power squared plus negative 3.86 times 10 to the negative 5th Newton. And then you also need to square the volume, and then you take the square root, which give us a volume of 8.638 times 10 to the negative 5th Newton. So this is the final answer. Problem 2. Proton in an atomic nuclei are typically 10 to the negative 15th power meter apart. What is the electric force of repulsion between nuclear atoms? So imagine you have two protons, and the distance between them is 10 to the negative 15th power meters apart. So what is the repulsion? What is the electric force of repulsion between the nuclear proton? So we know they are gonna repulse each other because they have the same charge, and their force can be calculated by using Coulomb's law. So 8.99 times 10 to the 9th power times charge. So proton has a charge of 1.6 times 10 to the negative 19th power Coulomb. And because you have two protons, so you need to times another 1.6 times 10 to the negative 19th power coulombs over their distance. And this should give you a volume of 230.14 Newton. So the force between them is equal to 230.14 Newton. Problem 3. Point charges Q1 is equal to 15 microcoulombs and Q2 is equal to negative 25 microcoulombs are placed 1.0 meter apart. What is the force on the third charge? Q3 is equal to 20 microcoulomb placed midway between Q1 and Q2. So here is Q1, 15 microcoulombs. Q2 is negative 25 microcoulombs, and Q3, 20 microcoulombs, and here is gonna be 0.5 meters, and here is also gonna be 0.5 micrometers positive charge, negative charge. So positive charge is gonna repel positive charge. So the 20 microcoulombs charge is gonna have a repulsive force by Q1 because they are both positive charge. And this one, Q2 is gonna attract Q3, right? So it's also gonna be a redward force. And let's call it F3. So now we can calculate F1 and F2. So F1 is gonna be equal to 8.99 times 10 to the ninth power times 15 times 10 to the negative 6th power times 20 times 10 to the negative 6th power over R square, so 0.5 square, which is equal to 35.96 Newton. And F2, so here this is F2, not F3. So F2 is gonna be equal to 8.99 times 10 to the ninth power times 20 times 10 to the negative 6th power times 25 times 10 to the negative 6th power. So we ignore the negative sign of the 25 microcoulomb charge because we know the force point to the right, so it gotta be a positive volume over R square, so 0.5 square, which is equal to 17.898 Newton. So the net force is gonna be equal to the sum of F1 plus F2, which give us a result of 53.94 Newton. So this is the final answer. Problem 4. Two small balls, each of mass 5 grams, are attached to a silk thread 50 meters long, which are in turn tied to the same point on the ceiling as shown below. When the balls are given the same charge Q, the thread hang at 5 degrees to the vertical as shown below. What is the magnitude Q, and what are the signs of the two charge? So since the ball are hang at 5 degrees to the vertical, it must be stationary, meaning the net force of the system must be equal to 0. So the ball here receive a force of gravity. G is equal to mg. Since it's 5 degrees, 5 gram, you gotta convert that to kilogram. So 5 divided by 1,000 times 9.81, which give us a volume of 0.04905 Newton. And we know the ball also receive a force of tension by the rope. And the rope is hung at 5 degrees. The tension can be separated into the vertical component, Ty, and the horizontal component, Tx. So since the ball is stationary, Ty must be equal to gravity, which is equal to 0.04905 Newton. Right. So let me redraw this picture a little bit. So since this degree here is 5 and those two lines are parallel, here must also be 5 degrees. Right? And we know Ty is also equal to T cosine 5 degrees. So we can calculate T. So T is going to be equal to 0.04905 over cosine 5 degrees, giving us a volume of 0.0492 Newton. So this is the force of tension. And now we can also calculate Tx. So Tx is going to be equal to T sine 5 degrees, which is equal to 0.00429 Newton. Right? So this is all the force we have right now. So let's redraw this force diagram. So let me erase this. I need to be careful with my So still let me draw it here. So the ball receives a force of gravity of 0.04905 Newton. A tension Ty of 0.04905 Newton. A horizontal tension of 0.00492 Newton. Well, if the ball is stationary, there must be another force F that is equal to 0.0492 Newton, but opposite in direction, right? So those two forces must have the same magnitude. So Tx, the magnitude of Tx must be equal to F. And this is Ty here. And this is gravity. So this force F must be the electric force. So electric force need to balance out, need to cancel out Tx, so the ball is in equilibrium. So let me write this down. So the magnitude of Tx must be equal to F, the magnitude of F. And we know the magnitude of Tx is equal to 0.00429 Newton. And we also know how to calculate electric force is equal to kq squared over r squared. And r is the distance here. So how do we calculate r? Well, we know the length of the rope is equal to 15 centimeters, which is equal to 0.5 meters. And we know it has a degree of 5. So here is going to be equal to 0.5 times sine 5 degree. And because there's another rope of 0.5 meters, which also have a degree of 5 degree to the vertical, and here is also going to be equal to 0.5 sine times sine 5 degree. So the total length r is going to be equal to 2 times 0.5 times sine 5 degree. So this will give us a volume of 0.0781516 meter. Right. So now you can calculate the charge Q. So 0.0492 Newton is equal to the Coulomb constant, kq squared over r squared. And we know the volume of r, so Q is going to be equal to r squared times 0.0429 over k. So which is equal to 0.08716 squared times 0.0492 over 8.99 times 10 to the 9th power. So this is equal to Q squared. So Q is going to be equal to the square root of this equation. Right. So let me calculate Q squared first. So Q squared will give us a volume of 3.625 6 times 10 to the negative 15th power, and Q will be equal to the square root of this volume. Which give us a volume of 6.02 times 10 to the negative 8th power was a unit of Coulomb. So this is the charge of Q. This is the magnitude of the charge Q. So what are the signs of the two charges? So we know for this charge here, it has electric force pointing to the right, and this force here if you do the force analysis, it must have a force pointing this direction, to the left direction. So it repel each other. So the sign of the two charge must be the same. The net-access charge on two small spheres is Q, show that the force of repulsion between the sphere is greatest when each sphere has an access charge of Q/2. Assume that the distance between the sphere is so large compared with their radii that sphere can be treated as point charges. So you have two spheres, sphere 1 and sphere 2. So let's say sphere 1 has a charge of nq, where n is between 0 and 1. Then charge 2, so charge on sphere 2 is going to be equal to 1 minus nq. And we know the force of repulsion is equal to kq1, q2 over r squared, where k is a fixed volume, so Coulomb constant, and r is super large, that they can be treated as point charge. So we don't really care about r and k here, since k is a fixed volume. So we only care about the numerator here. The force is greatest when q1 times q2 is greatest. So q1 times q2 is equal to nq times 1 minus nq, which is equal to nq minus n squared q. And then you can take q as the common term. So it's equal to k times n minus n squared. So q is a fixed volume. So when you need to find the volume of n, so that n minus n squared has the maximum volume. So I'm gonna wrote it this way. So negative n squared plus n times q. And here this part is a quadratic function. And because the sign is negative, it's gonna look something like this. So here will be the maximum volume. So for those of you who has learned calculus, you know here it has a slope of 0. So the derivative is going to be equal to 0. So you take the derivative, which is equal to negative 2n plus 1 is equal to 0. So n is going to be equal to a half, right? So n is a half. Then we know q1 is equal to q2 is equal to n q over 2. So this is why q over 2 is the correct answer. For those of you who have not learned calculus, you can solve this by using basic algebra. So let me erase this part. So this is a function here, and here is a maximum. So negative n squared plus n. So you need to find when does this function is equal to 0. So assume they are equal to 0, right? So is equal to negative n 1 minus n minus 1, sorry. So n can be equal to 0 or n is equal to 1. So here is 0 and here is 1. So here gotta be a half, right? So n is equal to a half. So now you know n is equal to 1 over 2. And when n is equal to 1 over 2, then q is gonna be equal to q over 2. So the charge q1 is equal to q2 is equal to q over 2. So this is why the force of repulsion is greatest when both sphere has a charge of q over 2. The charge of q is equal to 2 microcoulomb is placed at the point B as shown below. What is the force on q? So on the charge. So here is P, So here we know here has a negative sign here. I mean negative charge. Here has a negative charge. And P has a positive charge. So here the negative charge is gonna attract the positive charge. So it's gonna be a leftward force of F1, and the positive charge here is gonna repel this charge. So there's also gonna be a rightward force of F2. So here is Q. It's gonna have a leftward force of F1 and a rightward force of F2. And you can calculate F1 and F2. So F1 is gonna be equal to 8.99 times 10 to the 9th power times this charge here. So I'm just gonna take the magnitude first and then times this charge. So 2 microcoulomb, 2 times 10 to the negative 6 coulomb over r squared, so 1 meter squared. And then because it's pointing to the left, so it's gonna have a negative charge to represent a direction. And this should give us a volume of 0.05394 Newton. And now we can also calculate F2. So F2 is going to be equal to 9.88 times 10 to the 9th power times 1 times 10 to the negative 6th power, so 1 microcoulomb here, times 2 times 10 to the negative 6th power over r squared. So 2 plus 1 is equal to 3. 3 squared is equal to 9. And this should give us a volume of 0.001997, actually 8 Newton. Right. And now we can calculate the net force. So net force is gonna be equal to negative F1 plus F2. So because F1 is pointing to the right, so I'm just gonna write negative F1. Oh, I forgot the negative sign here. Well, actually let me write F1 since F1 has a negative volume here. So this is going to be equal to negative 0.05194 Newton. Two fixed particles, each of charge 5 times 10 to the negative 6 power coulombs, are 24 centimeters away. What force do they exert on the third particle of charge negative 2.5 times 10 to the negative 6 power coulomb that is 30 meters away from each other? So let's say here is the two fixed charge, charge 1 and charge 2. And then there's gonna be, and they are 24 meters away from each other. So there's gonna be another charge 3, which are 30 meters away from the two charges, charge 1 and charge 2. And charge 1 and charge 2 are positive, charge 3 is negative. So there's gonna be two attractive force. So the force is gonna be pointing this direction, F1, and this is gonna be F2. So let's draw a force diagram. So this is gonna be equal to F1. This is gonna be equal to F2, and F1 and F2 are equal in magnitude, since they are all 30 centimeters away from charge 3. So there's gonna be a vertical component, horizontal component, a vertical component, and a horizontal component. So the horizontal component cancels out. We only have two vertical components. So Fy is gonna be equal to 2 times F2y, which is gonna be equal to 2 times F1y. So because this is 24 centimeter here, you can, and charge 3 is in the middle of the line, so you can draw another line here. And here is gonna be 12 centimeter. Here is also gonna be 12 centimeter. So now that you have triangle like this. So you know the vertical component is equal to the net force, which is equal to 2 F2y. So now you just need to find F2 first, and then find the vertical component. So 2F2y is gonna be equal to 2F2. So let's say here is theta, cosine theta. So F2 is gonna be equal to 8.99 times 10 to the 9th power times charge 1, 5 times 10 to the negative 6 times 2.5 times 10 to the negative 6 over r squared. So 30 centimeter is equal to 0.13 meter. So I ignored the negative sign here because I'm calculating the magnitude of F2. But but for the vertical component, because it's pointing downward, it's gonna have a negative sign to represent the downward direction. But right now we are just calculating the magnitude of F2. So the magnitude of F2 should be equal to 6.6494 Newton. So this is the magnitude of F2. So now you need to calculate theta. So to calculate cosine theta, you need to know the length of this side. So this is gonna be equal to 30 squared minus 12 squared, and then take the square root, which is equal to 5. So cosine theta is gonna be equal to 5 over 13. So F2y is gonna be equal to Fy times 5 over 13, which is equal to 2.557 Newton. And because the force is pointing downward, you gotta have a negative sign to represent the direction. Now you can calculate the net force by multiplying this number by 2. So let me erase this a little bit. So F naught is gonna be equal to 2 F2y, which is gonna be equal to negative 5.1149 Newton. So this will be the answer for problem 7. Problem 8 asks, what is the force on the charge Q at the lower right-hand corner of the square as shown? So it's asking the force on this charge here. Let me change the color. Right. So what is the force? Well, since the other charge, they all have positive charge, there's gonna be 3 repulsive force acting on this charge here. So here is gonna have a downward repulsive force. We're gonna call that F1, and here is gonna have a horizontal repulsive force of F2, and here is gonna be a repulsive force of F3. And now we can calculate F1 and F2. So F1 is going to be equal to K times this charge, so Q square over A square, because it's pointing downward, it's going to have a negative sign. F2 is going to be equal to K times this charge, so also Q square over A square. Now we just need to calculate F3. So F3, you can separate F3 into different components. So we know this is a square. So here gotta be 45 degrees. And the horizontal component gotta be equal to the vertical component in magnitude. Right, so and cosine 45 degrees give us a volume of 1 over square root of 2. So now you can calculate F3x. So F3 is going to be equal to K times the two charges Q square over the radius square here. So R square is going to be equal to 2A square. Right. And then into times cosine 45 degrees. So times 1 over square root of 2. So this is F3x and F4x. So now let me redraw the picture here. So this is the positive charge. It receives a downward force of F2, a horizontal force of F3, a horizontal force of F3x. Oh, sorry, here is F2, I'm sorry. And a downward force of F3y. So you can calculate the x component of the force and the y component of the force. So when I say x component, I mean the sum of the horizontal force. So Fx is going to be equal to F3x plus F2, which is equal to KQ square over A square plus KQ square over 2 times square root of 2 times A square. Right. So I don't need this part here. And this will give us a volume of KQ square over A square times 1 plus 1 over 2 times square root of 2. So this is equal to the horizontal component. What about the y component? So Fy is gonna be equal to F1 plus F3y. So F1 is equal to KQ square over A square, negative KQ square over A square plus F3x. So F3x is pointing downward, so you're gonna have a negative volume. And here is only show the magnitude. So you're gonna be equal to negative KQ square over 2 times square root of 2 times A square. Right. So this is 2 here. And this is equal to negative KQ square over A square times 1 plus 1 plus 1 over 2 times square root of 2. So this is the y component, right? X component, y component. And now you can calculate the net force. So there are two ways of writing net force. The first one is this. So this is gonna be equal to KQ square over A square times 1 plus 1 over 2 times square root of 2 with a x naught, so meaning is horizontal direction, and then to plus the y component. So you're gonna plus, so let me erase this. So and then you're gonna plus, but because it's negative sign, so you're just gonna write negative. So let me minus KQ square over A square times 1 plus 1 over 2 times square root of 2 y hot. So this is one way of writing the net force. And another way is you can calculate the sum of the net force by using a Pythagorean theory. So this is equal to F net. So F net can be equal to the square root of Fx squared plus Fy squared, which is going to be equal to KQ squared times A squared. So I'm not going to plug all of the number in, but you know how to do it. So it's going to be equal to K squared times Q to the fourth power times over A times to the fourth power, 1 plus, and then you minus so this is another way of writing this, and you can simplify this equation. Oh, I'm sorry, here should be a positive sign because it's Fx squared plus Fy squared. And then you can combine the like terms together to get the answer. So you know that those two parts are same. So oops. So this is gonna be equal to the square root of 2k squared q to the fourth power over a to the fourth power times 1 plus 1 over 2 squared, which is equal to the square root of 2 times k times q squared over a squared times 1 plus 1 over 2 times square root of 2. So this is also the net force here. And this does make sense, right? Because when we were doing the force analysis, you know, and this equation here does make sense, right? Because when we were doing the force analysis, you should be aware that the horizontal component is equal to the y component, right? So the downward force is equal to the horizontal force in magnitude. And this force here, after you separate them into different components, the horizontal component is also equal to vertical component in magnitude. So if this force is F, this force is gonna be F, and then you can use force analysis. So the net force is gonna be something look like this. So this is F, and this is gonna be square root times F. So this is just two different way of expressing net force.